Hello everyone, my name is Ashwin Shirsat and I am a third year PhD student at North Carolina State University. Today, I will be describing a research titled Hierarchical Multi-timescale Framework for the Operation of Dynamic Community Microgrid. With changing climate conditions and we are increasingly facing the threat of global warming. This, along with human man-made attacks like cybersecurity threats, the chances of extreme impacts on the electricity grid are increasing with time. In the energy domain, such risks are by extreme weather events or cybersecurity threats fall on the high impact, low frequency spectrum, as you can see in the bottom left figure. Such events are not given the highest priority while designing these systems, but now they need to be prioritized since the frequency of them is increasing day by day. During any extreme weather event, a typical flow of planned tasks is to first plan how to handle the event, then absorb once an event occurs and recover from the event, and then adapt the system to handle these events in a better manner in the future, and continue this loop. Community microgrids play a vital role in doing this exact same thing, that is enhancing the resiliency of the system through this exact same approach. Hence, in this research, we focus on absorbing and recovering from such extreme weather events with the help of community microgrids. This is a typical structure of the community microgrids which have been integrated with the traditional distribution grids. So why do we need a proactive energy management algorithm? So during extreme events, we first lose the support from the upstream network. Once that is done, and plus this will result in long duration outages as well as limited generation resources available at hand. Further, we would also these low frequency high impact events would result in biased forecasts, since our forecasting algorithms are not designed to handle these kind of events due to lack of data, as well as increasing renewable energy dependence would then finally lead to higher forecast error impact. Hence, we need a proactive system that can be resilient and robust to these kind of to these events. So, in order to tackle these problems, we should make our system robust to forecast error, make the proactive decisions, schedule load curtailment properly, make sure there's optimal resource allocation, make the system hard enough to sustain for long duration outages, and the whole approach should be computationally efficient. And by making sure we attain all these things, we also should make sure that we maintain critical load priority. So for that, we present the hierarchical multi-timescale framework, which is a three-stage approach consisting of three cascaded state decision-making stages, which is the day ahead, near real time, and the real-time stage, used for taking these optimal decisions during an emergency situation. The underlying idea of this approach is that the forecasting error reduces as the time scale moves closer to the time of dispatch, and making sequential updates with newly obtained data will help make much more proactive and resilient decisions. Then, to balance the computational burden, we make sure that all the constraints are distributed respectively for each of the stages, given the amount of time that we have at hand to take optimal decisions. For example, the day-ahead decision is run much in advance, so it can be the most computationally burdensome stage, but the computational efficiency should go on increasing as we move towards real time. Hence, this table shows the optimal constraint distribution to make sure that the decisions are optimal. At the same time, they are taken in a computationally efficient manner. You can pause on this slide to see a more detailed model of the HMTS framework. To validate this approach, we test our HMTS framework on an IEEE 123 bus system, wherein we have partitioned it into a community microgrid by this green boundary, and the other external distribution grid shown in the red boundary and in the blue boundary. The results are shown here. So firstly, we can see that the non-critical load, almost 70% of that has been supplied, as in the critical load has been met 100%. This shows that we have prioritized critical load as well as maximized the non-critical load demand. Further, a vital aspect for comparison is how does our model outperform against the traditional two-stage approach, as well as under various forecasting error scenarios. This table here explicitly highlights the same. We can see that under different forecasting error scenarios, A to F, we have been able to supply 98% and above critical load and maximize the critical load as compared to the traditional two-stage approach. So some of the key takeaways have been summarized here, wherein we show that we have prioritized critical load supply, as well as our model outperforms the traditional two-stage approach and can smoothly handle different forecast error scenarios. So to summarize, we have been able to develop a system that can ensure secure operation of the microgrid as well as the external distribution grid, places emphasis on optimal resource rationing, can smoothly handle forecast errors, as well as outperform the traditional two-stage approach. This research would not have been possible through the support of US Department of Energy and from our industrial partners, Strata Solar and Wilson Energy. Thank you very much. If you have any questions, please feel free to email me at this email ID.